Okay, so this week we're going to look at 4.4 exponential and logarithmic equations. So on your notes it says day 1. We're going to do both in the same week. So first we're going to look at exponential equation. So an exponential equation is an equation containing a variable and an exponent. Some examples of exponential equations include 2 to the x power equals 32, or 4 to the x plus 3 power equals 64 to the x power, or maybe 2 to the x plus 5 power equals 3 to the x minus 7 power. So some exponential equations can be solved by expressing each side of the equation as a power of the same base. All exponential functions are one-to-one, that is, no two different ordered pairs have the same second component. So if b is a positive number other than 1, and b to the m power equals b to the n power, then m equals n. So what that's saying is if they have the same base, the exponents have to equal each other, which is the property that allows us to be able to solve these. So if we look at this first example, 2 to the 3x minus 8 power equals 16. So I'm going to rewrite the left-hand side because 2 is the smallest number that we can write a base as. So 16. So is there a way we can write 2 to some power and get 16? Well, that would be 4. So now, since we have the same base, these can kind of cancel, and we're left with 3x minus 8 equals 4. And then it's just solving a linear equation. So we add 8 to both sides. 4 plus 8 is 12. So 3x equals 12. Divide both sides by 3. And x equals 4. Alright, if we look at b, we have 27 to the x plus 3 power equals 9 to the x minus 1 power. So is there a number that we can rewrite so the bases are the same? So we can rewrite 27 as 3 to the third power. And this x plus 3 is just going to kind of hang out in parentheses with that. And we can rewrite 9 as 3 squared times the x minus 1 that was already there. So now that we have the same base, we can just look at our exponents. And I'm going to go ahead and distribute as we rewrite this. So 3 times the quantity x plus 3 is 3x plus 9. And 2 times the quantity x minus 1 is 2x minus 2. So if we wanted to solve this, subtract the 2x to the other side. 3x minus 2x is just x plus 9 equals negative 2. Subtract the 9, and x equals negative 11. Okay. So most exponential equations cannot be rewritten so that each side has the same base. So here are two examples. So one, let's see here, would be 25 to the x power equals 9 to the 2x plus 3 power. So we know we could rewrite 25 as 5 squared, and we can rewrite 9 as 3 squared. But again, that 5 and the 3 aren't the same, so they can't cancel. So we can't go any further. Okay, so another example would be 4 to the x power plus 3 equals 7 to the x minus 2. So again, we can't rewrite those so they have the same base. One thing you do have to be careful about is what if we had 3 to the x plus 4 power equals 1? Well, how can we rewrite 1 so it has a base of 3? Remember, this can be rewritten 3 to the x plus 4 equals 3 to the 0 power, because anything to the 0 power is 1. So now our bases are the same, so those can cancel. We're left with x plus 4 equals 0, so x equals negative 4. Okay, so that is one thing to be careful about, is that anytime it equals 1, you know you can just set your exponent equal to 0. Okay, so back to these examples here. So when we can't simplify using that exponential rule, this is when logarithms are going to come into play. So what we want to do is we want to isolate the exponential expression, and then we're going to take the common logarithm on both sides of the equation for base 10, take the natural logarithm on both sides of the equation for bases other than 10. So what we're going to do is we're going to simplify using one of the following properties. So if we have log of m to the p power, we're going to use the power rule, and we're going to move that p to the front, and that's going to allow us to solve. So, or if we have the natural log of m to the p power, that becomes p times the natural log of m. Okay, and then we just solve for the variable. So remember, if it's base 10, we use log, and if it is anything else, we use natural log. Honestly, those two can go back and forth. It's just dependent on also how it wants it written. Alright, so looking at our next page, looking at A. So 4 to the x power equals 15. So we can't rewrite that. So we have base of 4. I'm going to show you what it would look like if we did log. So if we take log of both sides, because what we do to one, we have to do the other. We can take the power rule, and we can move this x to the front, so that way we have x times log of 4 equals log of 15. And then since we're multiplying here, we can just divide by log of 4 on both sides. So x equals log of 15 divided by log of 4. And then if we wanted to plug that in our calculator, make sure that when you finish typing that 15, you close the parentheses before you start dividing. You should get x is approximately 1.953. Okay, so depending on how it's asking you on your homework, this would be your exact answer, and this would be your approximation. Alright, so looking over at D, so this is when log really comes into play. So we have 10 to the x power equals 120,000. So since we have base 10, when we take log of 10 to the x power equals log of 120,000, we have a rule that said log of 10 of anything is just going to cancel and just leave us with our exponent. So x equals log of 120,000. Okay, if we went ahead and plugged that in our calculator, we would get 5.079 if we rounded to the nearest thousandth. Okay, so that's one thing to be careful about on your homework, is making sure you're reading on what it wants you to round to in the end. Alright, looking at B. So 40 times e to the 0.6x minus 3 equals 237. So the first thing we always want to do is make sure we're getting anything that has like our base and our exponent completely by itself. So here that means this e to the 0.6x power, get that by itself. So let's start off by adding 3 to both sides. So 40 e to the 0.6x equals 240. And let's get rid of this 40 on the left by dividing it. So we have e to the 0.6x power equals 6. So since we have base e, anytime we have that e there, we always want to use our natural log. So if we take ln of e to the 0.6x power equals ln of 6, the natural log and the e are going to cancel. So we're left with 0.6x equals the natural log of 6. So we can divide by 0.6 on both sides. And we get x equals the natural log of 6 divided by 0.6. And if we plug that in our calculator, we get 2.986. Alright, going to the right. So very similar problem here. 7 times e to the 2x power minus 5 equals 58. We're going to start off by adding 5 to both sides so we can get our exponential portion by itself. And 58 plus 5 is 63. Divide by 7. So e to the 2x power equals 9. And then we're going to take the natural log of both sides. Our natural log of e is going to cancel. And we're left with 2x equals the natural log of 9. Divide both sides by 2. So x equals the natural log of 9 over 2, which is approximately 1.099. Alright, and looking at these last two examples, this is something very similar to what we looked at on the very first page of when we can't just use that exponential rule. So we have two different bases that we can't make look the same. Okay, so we have 5 to the x minus 2 power equals 4 to the 2x plus 3 power. So we're going to natural log or log, whichever you choose, both sides. For the sake of writing, I'm just going to use natural log. So we have the natural log of 5 to the x minus 2 power equals the natural log of 4 to the 2x plus 3 power. So we can put these in parentheses and we can move them to the front. Okay, so we have the quantity of x minus 2 times the natural log of 5 equals the quantity of 2x plus 3 times the natural log of 4. So here's where you have to be careful. So the natural log is just a number. So this is very similar to having x minus 2 times 3. Okay, what we would normally do is we would distribute, which is exactly what we're going to do here. So we're going to distribute this. So we get x natural log of 5 minus 2 natural log of 5 equals, distribute again, 2x natural log of 4 plus 3 natural log of 4. Just like any other equation, we want to get our x's to one side and our numbers to the other. So I'm going to subtract our 2x natural log of 4, move it to the left-hand side of our equation. So now we can't combine these two terms that have the x's because they have different logarithms. So x natural log of 5 minus 2x natural log of 4 equals, we're still writing, sorry. How about minus 2 natural log of 5 equals 3 natural log of 4. And then we're going to add our 2 natural log of 5 to both sides. So now we have x natural log of 5 minus 2x natural log of 4 equals 3 natural log of 4 plus 2 natural log of 5. So our x's are on one side and our number terms are on the other, but now we need to get rid of all the rest of this. So we're going to take out or factor out the greatest common factor of x, and we're left with the natural log of 5 minus 2 natural log of 4 equals this 3 natural log of 4 plus 2 natural log of 5, and then lastly divide. So x equals 3 natural log of 4 plus 2 natural log of 5 over the natural log of 5 minus 2 natural log of 4. Okay, and if you plug this in your calculator, which is something you have to be careful about, is making sure you put parentheses around the whole numerator and the whole denominator. And then remember, after every natural log or log, the parentheses open, so make sure you're careful to close them each time. Okay, so if you plug that in, x is approximately negative 6.343. Okay, so if we do the second one, well, it's very similar to that. So 3 to the 2x minus 1 power equals 7 to the x plus 1. Again, I'm going to natural log both sides. And then move those binomials to the front using our power rule. Okay, we're going to distribute. So 2x natural log of 3 minus the natural log of 3 equals x natural log of 7 plus the natural log of 7. And then we're going to move our x terms to one side. So we have 2x natural log of 3 minus x natural log of 7 minus the natural log of 3 equals the natural log of 7. Add our non-variable term to the right side. So we have 2x natural log of 3 minus x natural log of 7 equals the natural log of 7 plus the natural log of 3. And then factor out the x. And divide. So x equals the natural log of 7 plus the natural log of 3 divided by 2 natural log of 3 minus the natural log of 7, which is approximately 12.114. All right, and looking at our next page, exponential equations. Oops. So we're revisiting our interest formulas. So remember the formula, A equals P times the quantity 1 plus R over N to the NT power. Describes the accumulated value A of the sum of money P, the principal, after T years at annual percentage rate R in decimal form, compounded N times a year. So, how long will it take $25,000 at 9% annual interest compounded monthly, and this should say to double? Okay, so we're going to just start off with stating everything we know. So how long will it take $25,000? So that's how much money we're starting with. So that's our p-value. At 9% annual interest, so R equals 0.09, because we're going to change it to a decimal. compounded monthly, so that's our n. So how many times does monthly occur in a year? That would be 12. And then to double. So if we double the amount of money we started with, we would have $50,000. And we asked how long. So t is what we're solving for. So if we plug everything in that we know. So A equals our 50,000, which equals P, so 25,000, times the quantity 1 plus 0.09 divided by 12 over 12 times t power. So start off with getting, we're going to get this expression by itself. So we're going to divide by this 25,000. And that gives us 2 equals 1 plus 0.09 divided by 12 to the 12t power. So the thing you want to be careful about when you're doing this is if you take 0.09 divided by 12, I didn't do that part. Hold on. 0.09 divided by 12. We actually get a nice decimal. A lot of times you're not going to. So if you want to go ahead and do that, we get 0.0075. If we add that to 1, we get this. Okay, so as long as your decimal terminates, it's okay to rewrite it. If it doesn't, you want to leave it. Okay, so now we're going to natural. Actually, let's log both sides on this one. So if we do log of 2 equals log of 1.0075 to the 12t power. And again, it doesn't matter if you do log or natural log. Honestly, I'm doing log because that's what I have written down on my paper. So using our power rule, so log of 2 is going to stay the way it is. Then 12t log of 1.0075, because we took that exponent, we moved it to the front. And then we're getting t by itself. So we're going to divide by everything that's not t. So 12 log of 1.0075. So t equals log of 2 divided by 12 log of 1.0075. And you're plugging that in your calculator, make sure you're putting parentheses around your denominator. And if you plug that in, you get approximately 7.7. And remember, we're talking about time in terms of years. All right, and we're just going to set up this last one. So how long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? So we started off with $1,000. We want it to grow to be $3,600 at a rate of 8% or 0.08 compounded quarterly. So quarterly, how many times does that happen in a year? 4. So if we plug into our formula, we would have 3,600 equals 1,000 times the quantity 1 plus 0.08 divided by 4 to the 4t power. And I guess we can go ahead and finish this one. So if we go ahead and divide by 1,000, we get 3.6 equals, and if we go ahead and calculate this, I'm thinking it's 1.02, but let's double check. Yep. So 0.08 divided by 4 is 0.02 plus 1 gives us 1.02 to the 4t power. Here let's do log of 3.6 equals log of 1.02 to the 4t power. We're going to move our exponent to the front. So we have log of 3.6 equals 4t log of 1.02, and then divide both sides by 4 log of 1.02. So t equals log of 3.6 divided by 4 log 1.02. And I have not done that calculation. I don't have my calculator near me. So extra credit if you email me the answer. So I'm going to break this video into 2 parts, just for the sake of trying to load it and for you guys to be able to watch it.